Hi, I'm Vince Stueve and welcome to Micrel TV. I'm an FAE here at Micrel, and today we're going to discuss our Hyper Light Load and LowQ buck regulators. This video assumes you already know how a buck regulator works, so if you don't know how a buck regulator works, there's other videos out there and you can view those. Take a look and understand how the bucks work first. But let's jump into this. So what is Hyper Light Load? When we say Hyper Light Load at Micrel, what we mean is light load efficiency. A normal buck would follow this line I'm showing right here, the pink line. The efficiency drops off way down to 30% at 1 milliamp out. With a Hyper Light Load buck, our efficiency will stay up around 85, even 90% on some parts, as low as 1 milliamp output current. You can see there's an inflection here, and this is where the part changes from being a continuous mode to a discontinuous mode buck. The eval boards for these parts use the small part along with chip inductors and small ceramic capacitors to generate your output voltages. This slide shows you the performance and efficiency of various input voltages for a 1.8 volt output. In this blue region is where the part is in continuous mode. As the part senses current on the output gets lighter, it switches over to a hysteretic buck mode, and this is the discontinuous mode, and this is how efficiency is kept very high, even at 1 milliamp out. When we look at the switching frequency, this graph is the same scale as the previous graph, but we're showing the output frequency. The output frequency of the part is 4 megahertz until it senses that current is getting light. At that point, here at about 70 milliamps on this part, it switches into a hysteretic mode. You can move the knee of where this inflection point occurs over to the left on the curve by changing the value of the inductor. This is a scope shot of the 23250 regulator running at 300 milliamps output current. Notice that the output voltage shown on the top trace is only 3 millivolts of ripple. We're in continuous mode here, so we're putting out 300 milliamps. The next slide I'm showing, we're doing 150 milliamps. You can see we're still in continuous mode and there's 3 millivolts of ripple. This slide shows 10 milliamps. The switch node in the middle is now just pinging on every once in a while. What happens in Hyper Light Load mode is that the part becomes hysteretic. It only switches the topside MOSFET when necessary, sending bursts of energy out to the output capacitor. That results, if you look back at the graph, in a little bit more ripple on the output. You can see in this case we have 18 millivolts of ripple. The switcher comes on, it charges up the output cap, and then it discharges until it's ready to recharge that capacitor. Now if we look at the part with 1 milliamp output current, you can see we're just pulsing it every once in a while. And still, this is only 18 millivolts of ripple. 18 millivolts for a 1.8 volt output is still only 1% of the total value. Next, let's take a quick look at the load transient response. This is a load step from 1 milliamp to 150 milliamps on the output. You can see as soon as we go to continuous mode, we have a nice 3 millivolts of ripple on the output, and then back to lightly loaded. The total change here is around 23 millivolts in this graph. Next, let's go to LowQ mode, and let's talk about what happens in LowQ mode. Here you can see a part, the MIC 3385. This part happens to have an internal inductor. The internal inductor is connected to the synchronous buck regulator, and during normal operation we're just running as a buck to the output capacitor. There's a LowQ pin on this part, and when you engage LowQ, it turns off the switcher and engages the LDO. Now you go from being a switching regulator to an LDO. You almost can't tell the difference between being in a switching mode and LDO mode, except for the fact that the quiescent current goes down to 18 microamps when you're in LowQ mode. The other part that's an extension of all these families is called a HELDO. It's a high efficiency LDO. A HELDO, as shown here, has an internal inductor. We run this right at saturation and then go out of the part and come back into a post-regulating LDO. The post-regulating LDO cleans up all the noise off the saturated inductor and presents it out to the user. These parts can allow you to use a minimal footprint to realize a very, very clean supply. As low as 3 millivolts of ripple at full load out is possible. Shown here is a table of the Hyper Light Load, LowQ, and other parts Micrel makes for low voltage conditions. This table shows the parts that we offer for Hyper Light Load, LowQ, and HELDO that have internal inductors. These parts are very nice in systems because they reduce emissions off of normal switchers by having internal inductors. This is an X-ray of the MIC 33153. This is a 1.2 amp buck. It has an enable pin, a soft start pin, and it also has a power good output. This allows you to make a completely sequenceable system with just a 4.7 microfarad on the input and a 4.7 microfarad on the output. It looks almost like an LDO, but it's a switcher. Well, thank you for your time in viewing the video. We hope that's helpful in understanding Hyper Light Load and LowQ mode. For Micrel TV, I'm Vince Stueve. Thank you.